Hello everyone, I'm Leah. Today, we're diving into advanced machine learning techniques for environmental modeling. In this module, we'll explore how machine learning can help us analyze and predict environmental trends, from air quality to climate change projections. By the end of this session, you'll understand several key machine learning techniques, their applications in environmental science, and how we can evaluate and improve these models for reliable predictions. Let's start with our learning objectives for today. First, we'll look at different machine learning algorithms and how they're applied to environmental data. We'll also discuss environmental models used for forecasting trends, such as temperature changes and CO2 emissions. Lastly, we'll learn how to build predictive models to address specific environmental challenges like deforestation or pollution. By the end of this lecture, you'll have a solid understanding of these techniques and know how to evaluate and optimize models for real-world applications. Supervised learning for environmental data. We'll start with supervised learning, a type of machine learning where a model is trained on labeled data to make predictions. In environmental science, we use supervised learning for tasks like classification, categorizing data points into specific groups, and regression, predicting continuous values. Classification could involve predicting whether a region is urban or rural based on satellite imagery, while regression is often used for forecasting variables like temperature or pollutant concentration over time. Supervised learning is particularly powerful because it enables us to make informed predictions based on historical data. Techniques in supervised learning. Let's break down these two key supervised learning techniques. Classification. This technique helps us predict discrete categories. For instance, we might classify areas by pollution levels, e.g. high, medium, or low, based on air quality data. Regression. This technique is essential for predicting continuous values, such as estimating future CO2 levels. For example, we might use a linear regression model to analyze the relationship between CO2 emissions and temperature rise over decades. These techniques form the backbone of predictive modeling for many environmental challenges, from pollution prediction to species distribution analysis. Case study: Predicting Air Quality Index, AQI, with machine learning. To see how supervised learning can be applied, let's examine a case study on predicting the Air Quality Index, AQI. Data source. We use daily measurements of air pollutants like PM2.5, PM10, and various gases. Modeling approach. Using regression, we train the model to predict the AQI based on pollution levels and weather data. The model could be further enhanced by adding variables like wind speed or traffic density for urban areas. Outcome. By accurately predicting AQI, cities can issue alerts and take measures to reduce exposure during high pollution periods. Reliable AQI predictions ultimately support public health by enabling proactive responses to pollution events. Unsupervised learning in environmental data. Next, let's move to unsupervised learning. Unlike supervised learning, unsupervised learning doesn't require labeled data. Instead, it identifies patterns within the data. The two main techniques we'll discuss are clustering and dimensionality reduction. Clustering groups data points based on similarity, which is useful for identifying areas with similar pollution profiles. Dimensionality reduction, on the other hand, simplifies large datasets by reducing the number of variables, making it easier to visualize complex data. Clustering for environmental data. Clustering is a valuable tool for many environmental applications. K means clustering. This technique groups data points into clusters based on similarity. For instance, we can use k-means to identify regions with similar air quality characteristics and categorize them by pollution levels.
Hierarchical clustering. This method creates nested clusters, which can be useful for grouping regions based on biodiversity, for example, by species or ecosystem type. An example application would be clustering regions based on pollution data to identify high-risk areas and develop targeted interventions. Dimensionality reduction. Principal component analysis, PCA. Let's talk about Principal Component Analysis, or PCA. PCA is a technique used to simplify large datasets by reducing the number of variables while preserving essential patterns. PCA is extremely useful in environmental data analysis, where datasets can have hundreds of variables. By applying PCA, we can transform these variables into a smaller set of components, making it easier to visualize and analyze patterns without losing critical information. For example, PCA can simplify a biodiversity dataset to highlight the main factors influencing species distribution. Time series forecasting for environmental data. Now, let's discuss time series forecasting, which is essential for predicting future environmental trends based on historical data. This type of analysis is commonly used in climate science to forecast temperature, CO2 levels, and deforestation rates. Time series forecasting can be linear or nonlinear, depending on the patterns in the data. In this section, we'll look at two techniques, ARIMA and LSTM. Techniques for time series forecasting. ARIMA and LSTM are popular time series forecasting techniques. ARIMA, Autoregressive Integrated Moving Average. ARIMA works well with data that has a linear trend or seasonality. For instance, we might use ARIMA to forecast monthly CO2 levels based on past patterns. LSTM, Long Short-Term Memory. Networks. LSTM is a type of neural network suited for complex time series data with non-linear patterns, like those found in climate models predicting temperature rise. Each of these methods is useful for different data types. ARIMA is simpler and faster, but limited to linear patterns, while LSTM can capture more complex patterns, but requires more data and computational power. Hands-on project, forecasting climate change trends. To illustrate, let's consider a project on forecasting CO2 concentration in the atmosphere. Objective: we'll aim to predict CO2 levels over the next 5 years. Dataset: using a historical dataset of monthly CO2 levels, we'll apply ARIMA and LSTM models. Steps: first, we pre-process the data, then train both models and compare their predictions. This comparison will help us understand which model is best suited for long-term forecasting of CO2 trends. By the end, this project will give us insights into how CO2 levels might change in the coming years, which is valuable for climate action planning, model evaluation, and tuning. Once we've trained our models, we need to evaluate their accuracy. Key metrics include RMSE, root mean square error. This measures prediction error and is commonly used for regression tasks. Accuracy. In classification tasks, accuracy represents the percentage of correct predictions. Precision and recall. For imbalanced datasets, such as detecting rare pollution events, precision and recall are especially useful metrics. These evaluation metrics help us understand how reliable our model predictions are, guiding us in refining and tuning the model as needed. Model tuning, cross-validation, and hyperparameter. Tuning. To improve model performance, we can use cross-validation and hyperparameter tuning. Cross-validation divides data into multiple subsets for training and testing. This process helps us better understand the model's performance and avoid overfitting. Hyperparameter tuning involves adjusting model parameters to find the best configuration. We can use methods like grid search or random search to optimize parameters, such as the number of clusters in k-means or the learning rate in neural networks. Effective tuning ensures that our models are optimized for the best possible performance, making them reliable for real-world applications. Let's summarize what we covered today. We began with supervised learning techniques for regression and classification, followed by unsupervised learning, where we discussed clustering and dimensionality reduction. We then explored time series forecasting with ARIMA and LSTM methods, and concluded with model evaluation and tuning techniques. Machine learning offers powerful tools for predicting and analyzing environmental trends, making it essential for informed decision-making in environmental science. In conclusion, advanced machine learning techniques are indispensable for modeling environmental data and forecasting trends. These models can provide valuable insights that help policymakers, researchers, and environmental organizations take proactive measures to address issues like air quality, climate change, and biodiversity conservation. Thank you for your attention. Now, let's open the floor for questions. I'd be happy to clarify any concepts or discuss how these techniques could be applied to environmental issues you're interested in. Put your answer in the comments.